Automatic repeat request is a method to ensure data transmissions (ARQ) work by using acknowledgements and have a timeout to detect lost or corrupted packet. This method used to avoid any packet loss in acknowledgements, but if acknowledgements not receive any packet, it will be retransmit the lost data. This method to improve communication accuracy without requiring perfect transmissions channels. There's a three type of ARQ that used in networking protocols, wireless protocols, and data links layers for maintaining data decency. The first one is stop and wait, go backend, and also selective repeat. Okay, we go the first one, go backends. Go backend is a technique used sending some packet continuously without waiting for acknowledgements for every packet before sending another packet. Go backend work sender will send the packet until n number together, where the n size have a window size for every packet have a sequence number. Sender will keep the copy of the packet before acknowledgements. If the receiver did not accept any packet, the sender will send again. The second one is stop and wait. Stop and wait is a basic protocol in ARQ for reliable data across noisy channels. Stop and wait protocol is ensure reliable data transfer by using error detections and retransmissions principles and retransmit sends a data message receiver. After that, it will stop and wait acknowledgements from the receivers. This process continues until an error-free acknowledgement is received. The protocol uses a sequence number in the header for both data acknowledgements message to distinguish between the new message and a duplicate. The last one is selective repeat. A protocol used in RQ blocks are numbered and sent to the receiver. The receiver acknowledge or negatively acknowledgements each block by number. The receiver must be capable of storing at least S block where S in the storage capacity of the data link. This allows block to be delivered continuously in a correct order following an error. The throughput of a selective repeat system with the infinite receiver buffer and block error probability P is 1 minus P, which is equal to the channel capacity. However, real receiver have finite buffer, which can lead to buffer overflows and reduce throughput in high error rate conditions.
So now I'll walk you through the performance analysis of three key data transmission protocols: stop and wait, go backend, and selective repeat, under the condition of low packet loss and high bandwidth. Let's begin with the throughput result on the top left. As we can see, go backend with 1% packet loss achieved the highest throughput, reaching nearly 6%. This is a sharp contrast to the stop and wait protocol, which shows consistently low throughput regardless of packet loss levels. Selective repeat performs moderately but doesn't quite reach go backend and lower loss level. Moving to the total transmission time. Protocols like stop and wait experience high latency with times above 1 second. In contrast, go backend with 1% loss completes transmission in just 0.2 seconds, make it the fastest and most efficient option in this environment. On bandwidth utilization, the trends are similar. Go backend again leads, utilizing about 0.6% of the available bandwidth. Stop and wait barely makes a dent in bandwidth usage, highlighting its inefficiency in high bandwidth scenarios. Now, shifting to the bottom row, we look at processing overhead. As expected, selective repeat, especially with higher packet loss, shows the highest overhead, reaching over 15%. This is due to the added complexity of managing out-of-order packets and individual acknowledgement. Finally, the retransmission count shows a clear relationship with packet loss. Selective repeat at 10% results in the highest retransmissions, while stop and wait at 1% stays near the bottom. However, despite more retransmission, selective repeat still maintains better throughput than stop and wait. So for the conclusion, in an environment with low packet loss and high bandwidth, go backend outperforms the others in terms of throughput, transmission time, and bandwidth utilization, while selective repeat is more reliable but comes with a cost, which is higher processing overhead and retransmission count as increased packet loss. Stop and wait, while simple, is highly inefficient under this condition and unsuitable for high performance needs.
Hello everyone. Today we will be discussing the comparison of different ARQ protocols under tough network conditions, specifically when there's high packet loss and limited bandwidth. In this slide, you'll see 5 graphs that compare the performance of stop and wait, go back N, and selective repeat. Let's start with throughput. As expected, stop and wait has the lowest throughput. It sends one packet at a time and waits for an acknowledgement, which really slows things down when there's a lot of packet loss. Go back N does a bit better since it sends multiple packets before stopping. But if one packet gets lost, it still has to retransmit a whole bunch. The best performer here is selective repeat, which only retransmits the packets that were actually lost, so it's way more efficient and keeps the data flowing. Next is total transmission time. Here, the trend is pretty clear. Stop and wait takes the longest, while selective repeat completes the transmission the fastest. Again, that's because it avoids unnecessary retransmission and keeps the pipeline full. Moving on to bandwidth utilization, we see a similar pattern. Stop and wait performs poorly. It spends a lot of time waiting. Go back N uses the bandwidth better, but selective repeat really makes the most out of what little bandwidth is available, which is crucial in this kind of scenario. Now for processing overhead. This one flips a bit. Stop and wait is the lightest in terms of processing because it is super simple. Go back N and especially selective repeat has higher overhead because they need to keep track of multiple packets and acknowledgements. But that extra effort pays off in overall performance. Lastly, looking at the retransmission count, Go back N has the highest since it resends all packets after a lost one. Stop and wait is in the middle and selective repeat has the lowest because it only resends what's necessary. So in conclusion, even though stop and wait is simple and lightweight, it doesn't just hold up under high packet loss. Go back N is a step up, but it's still not very efficient when packet loss is high. Selective repeat clearly stands out as the best choice as it gives the best throughput, fastest delivery, uses bandwidth well, and keeps the retransmission low. That's all. Thank you.
Now I'm gonna explain about throughput. The selective repeat consistently offer the best throughput, especially at 150 milli per second and 300 milli per second times out, reaching over 2%. Stop and wait performance worse because it's showing very low throughput due to its inefficient waiting. And the second one is processing overhead. Stop and wait has the highest overhead, around 15%, while selective repeat keeps the overhead low, especially at longer timeouts. The third one is bandwidth utilization. Again, a selective repeat leads, reaching at 0.23 utilization at 150 milli per second. Then, its stop and wait struggles, staying below 0.1 regardless of timeout. So, bottom row explanation, which is the time and reliability, transmission time, is have selective repeat finish transmissions faster than others, around 0.4 to 0.6 seconds. Stop and wait is the slowest, especially at 15 millisecond times out. And the retransmissions counts. For the retransmissions count, stop and wait go and back require more retransmissions, especially at shorter times out. Selective repeat reduces transmissions needs. At particulars, at 150 and 300 milli per second. So overall, selective repeat performance the best across all time intervals, especially in high latency environments. It achieves higher throughput, better bandwidth use, and lower retransmission, making it more suitable for modern and delay-sensitive networks. On the other hand, stop and wait perform poorly and mainly due to idle waiting times and limited packing handling.
Hi, my name is Muhammad Arif Bizanuddin. My metric number 105175. I want to present a scenario for bring Windows site for go back N and selective repeat ARQ. So this is a fixed parameter. The total packets I use is 1000 packets. The packet loss is 5%, SK loss is 2%, and the bandwidth is 5 megabits per second. Latency 100 milliseconds, timeout 500 milliseconds, and the video size I use is 4, 8, 32, and 54. So I use 1000 packet because 1000 packet are used as a common packet that many research papers and textbooks use. And 1000 packets also is a default total packet when you use the network simulator tools like NS2 and NS3 in many research papers. So I use the fixed parameters that I choose it based on the real use case scenario, which is the quality of network of IoT in rural areas. So the packet loss probability is 5% or 0.05. Packet loss is 5% because of the weak signal due to environmental interference, including trees and hills, and even causing the packet drop or delay. And the uplink, I mean the sender to the receiver, using a low battery, which is it use the weak signal to send the data packets. And the SK loss is 2%, the lower than the packet loss probability. The downlink is divide the received data, send the FTK packet using larger and wider infrastructure facility. So when the receiver send STK packets to the sender, it will use the alternate route in network by using the larger and wider infrastructure like antenna tower in the rural area. Bandwidth is a 5 megabits per second. It's considered low because in the rural area, there's not so much packet can be successful to deliver to the sender or receiver. So the 5 megabits per second is enough for the network in the rural area. So the latency is 100 milliseconds. Latency is the estimate travel time for sending data packets from sender to the receiver. So latency is quite high for a 100 milliseconds because the packet must be through the rural area. That means it will have many interference like forest and hill. So it will take longer time for packets to arrive from the sender to the receiver. So timeout is 500 milliseconds. So the timeout time must be higher than latency and RTT, round trip time. The RTT is the travel time of data packet from sender to receiver, and the travel time of SDK packet from receiver to sender. If the timeout time is same as latency time, so the premature retransmission will occur. I mean, the transmission will happen before all the packets will arrive to the sender from the sender to receiver or receiver to the sender. And it is too risky to retransmit even though packets are delayed. A larger timeout gives the network more time to recover and deliver SKs. So this is an output C program for go back N ARQ by the Windows side, and this was selective repeat ARQ. So all the output are recorded in the table based on performance metrics, throughput, total transmission time, bandwidth utilization, processing overhead, and the transmission count. And the records will make it to the graph based on performance metrics. Next, for analysis and discussion, for throughput. Throughput is the how much data is successfully sent or received in the network. So the go back and RQ, you have a low throughput because you need to wait the last data packet to arrive before the window can sliding. So the go back RQ is the like it must be follow the order, like the NX order from 1 to 5. So if the 5 packet, if the 2 packets arrive and the 4 and the if the 1, 2, 4, 5 is successfully arrived, but 3 have error, so it must be sent from 3 to 5 packets to retransmit from the sender to the receiver. So it need more time. So because of that, it will have the less data successful delivered. And the selective repeat RQ, you have the greater throughput because the larger window packet allow the more data packets for sender to the receiver. And because of when in the selective repeat RQ, the sender can send data packet as long as within the sender window. So the more data successful delivered. And for bandwidth utilization, in a go back and RQ, you have a low bandwidth utilization. The bandwidth utilization is the how efficient the usage of the bandwidth. So in the go back and RQ, you have the low bandwidth utilization because the longer time to wait to retransmit the data for the window to start make the bandwidth wastage. I mean, if the lower window size, so the window small group of packet will be arrived for sender to receiver. So in each small group of the packet, it will have the error for each small group. So each small group will retransmit over and over again, so it will make the longer time to wait to retransmit the data. In selective repeat RQ, you have the higher bandwidth utilization. Receiver can send SDK packets to sender even out of order, and sender can send new packets data to receiver as long as within the sender window. Processing overhead is how much extra work need to do by the network to manage a task. So in the go back and RQ, processing overhead decrease as window size increase. It's because the sender SDK packets together simplify the process even the window size are larger. I mean, if in the go back and RQ, the window size of packets, the transmission will keep happen because of the small group of packets will retransmit and over again. And the selective repeat RQ, the processing overhead increase as the window size decrease. Selective repeat RQ, it will acknowledge SK packets by individually packets. By means, if the larger group of packets arrive, so the larger process for SK packets to be acknowledged. And it will make the processing overhead will be high as the window size increase. Total transmission time is total time the data sent from the sender to the receiver. So in the go back and RQ, the high transmission time as the window size increase. So the error becomes more frequent and the unnecessary sense of good packets with lower window size causing increasing time delay. So like that is the processing overhead. The transmission will keep happen in the go back and RQ. So the time transmission will be high. Selective repeat RQ, you have slightly lower than go back and RQ because the protocol just retransmits the necessary packets only. So it makes it slightly faster than go back and RQ. So the transmission count. If transmission count is how many times the data will be retransmitted. So in the go back and RQ, the higher transmission count as the window size increase. I mean, the presence of even a single error can significantly increase the transmission count. The selective repeat RQ, you have a lower retransmission count. If a frame is lost or corrupted, only the specific frame is retransmitted, so it's resulting in fewer retransmission. So by means, in the go back and RQ, the transmission will be high because of if the one single packet error, it will send the all packets onward to retransmit from sender to receiver. In the selective repeat RQ, it will send only the packet error only to retransmit from the sender to receiver. So in summary, if selective repeat RQ performs better than go back and RQ, it minimizes retransmission by only resending lost or corrupted packets. It minimizes throughput by allowing continuous data flow even if some packets fail. Larger window size improve efficiency but increase capacity. High latency and packet loss degrade go back-end performance more severely than selective repeat. For unreliable networks with big signals and low bandwidth, selective repeat is the better choice due to its efficiency. Go back-end is simpler but wastes bandwidth with unnecessary retransmissions. These findings help optimize protocols for real-world scenarios like IoT, OSSs, and congested networks.
Okay, now we go to part B for Narmi Sendirian Berhad diagram network. The diagram show of Narmi Sendirian Berhad. We have two offices, Office A and Office B. For Office A have 15 computers, 5 mobile users, and 1 Wi-Fi for guests. For Office B have 10 computers, 3 mobile devices, and 1 Wi-Fi for guests. The infrastructure begins with the internet connection provided by an internet service provider, which is linked to a modem. From the modem, the connection is passed to a router that handles IP address assignments and manages the internet traffic routing. A wireless access point for mobile users, shared printers, and several desktop PC connected by internet are depicted in Office A design. There is also central distributions unit which probably serve as an internet resource center or file server. Additionally, there is a separate guest Wi-Fi access point called Wi-Fi for guests, which allow guests to access the internet while separating them from the office network. These diagrams also work same as like for Office B. Thank you.
Diagram explanation. The diagram shown of Narmi Sendirian Berhad where we have two Office A and Office B. For Office A have 15 computers, 5 mobile users, and 1 Wi-Fi. Office B have 10 computers, 3 mobile devices, and 1 Wi-Fi guest. The infrastructure begins with an internet connection provided by an internet service provider ISP, which is linked to a modem. From the modem, the connection is passed to a router that handles IP address assignment and manage internal traffic routing. A wireless access point for mobile users, shared printers, and several desktop PCs connected by Ethernet and depicted by Office A's design. There is also a central distribution unit which probably serves as an internal resource center or file server. Additionally, there is a separate guest Wi-Fi access point called Wi-Fi for Guest Office A, which allows guests to access the internet while separating them from the main office network. For Office B, same like Office A.
For our network setup, we are using C86 Ethernet, which is a great choice, especially since both Office A and B are located in the same building. This makes it easy and affordable to install the Ethernet cables without needing complex infrastructure. C86 cables are known for their high performance. They operate at 250 MHz, which means they can handle faster speeds and have lower signal interference. They support data transfer rates of 1 Gbps and even higher, which is more than enough for most internet service providers. Another big advantage of using C86 Ethernet is the low latency and high reliability. Compared to wireless connections, Ethernet offers faster data transmission with fewer delays and much lower chances of packet loss, making it ideal for stable and efficient communication between the offices. C86 Ethernet is also a practical choice because it offers better signal protection. The twisted pair wires inside the cable helps to reduce electromagnetic interference, which is also known as EMI. It is common in office environments full of electronic devices. It also has a thicker outer sheath that helps prevent near-end crosstalk and blocks external noise. This improves the overall connection quality. This also makes C86 Ethernet ideal for office use, where a stable and secure connection is important for smooth and reliable daily operation.
Hi, my name is Dayang Nonalia binti Abang Hussein, and my matric number is 103811. Now I'm gonna explain about Cat6 Ethernet. Cat6 Ethernet is a cost-effective network solution that offers a great balance between performance and affordability. The pricing is competitive, with reels available at approximately 1,590.20 cents and per meter cost starting from 5 ringgit 20 cents. It's depending on the cable type and installation quality. This makes Cat6 an economical option for both small and large deployment. In terms of installation, Cat6 is highly favorable because the setup is straightforward and considered as standard practice among IT professionals. This required no advanced or specialized tools are required for basic termination or installation, which reduce the overall setup costs. This accessibility not only cuts the expenses, but also shorten the deployment time and making it ideal for businesses looking to upgrade or expand their network quickly and affordably. For the second slide, we're gonna explain about future-proof and performance-oriented. For this slide, Cat6 Ethernet cables are designed to support high-speed data transfer, handling up to 10 gigabit per second bandwidth for distances up to 55 meters. This performance makes them well suited for modern business environment, including Narni Sendirian Berhad, which currently operates at 500 megabit per second downlink and 300 megabit per second uplink speed. The capability of Cat6 far exceeds this requirement, ensuring that the infrastructure is prepared for future upgrades without needing to replace the cabling. Its future-proof nature also means that as network demands grow, Cat6 can scale accordingly. For example, if the required cable length exceeds 55 meters, switches can be added without performance degradation. This makes Cat6 not only smart investment today, but also a reliable foundation for years to come.
Hi, my name is Muhammad Arif Bezaduddin. My matrix number is 105.75. I want to present the switch that we use in the network technology. So the name of switch that's suitable for Narni neighborhood is TP-Link TLSG1048. Practically, it has 48 ports. It can support 25 PCs, 1 router, and 2 access points. It can avoid complications of linking multiple switches. It reduces potential network errors and simplifies management. It will provide gigabit per speed per port that will improve efficiency for daily office tasks. And for the cost of effectiveness, the price range in Malaysia is 700 to 900 ringgit. Only one unit needed for current usage, and extra cost available for future device expansion. So that's all for us. Thank you.